Hello, Boston. I'm George from the Technical University of Munich, and I'm here to talk about our work on bounding data reconstruction attacks with the hypothesis testing interpretation of differential privacy. So without further ado, let me share my screen. So this is joint work with my colleagues from TUM and Imperial College, and also from Google DeepMind. And you can find our paper at the archive tag, which is shown at the bottom of the slide. Let me briefly discuss the motivation of our work. As you may know, differential privacy's guarantee is canonically sort of associated with bounding the success of membership inference attacks. In fact, it's possible to interpret the differential privacy guarantee entirely in terms of the hypothesis testing errors of an optimal membership inference adversary. And you might have heard of this under the moniker of FDP. Now, membership inference resilience is a most significant bit property. That means that all weaker attacks than membership inference are automatically also bounded in their success. Now, as you can imagine, data reconstruction attacks, where we have to reconstruct many more bits than just the membership bit, are much harder. And thus, it's possible to actually bound them with much looser privacy budgets than we would need for successfully constraining the success of membership inference attacks. In our work, we furnish closed-form bounds on the success of data reconstruction attacks using the hypothesis testing interpretation of DP. Let me give you just the briefest background on the hypothesis testing interpretation in case you're not familiar with it. Under this interpretation, we assume that an adversary observes a mechanism output Y, and they establish two hypotheses. One is called the null hypothesis, age 0, which is that the output Y was generated from the mechanism acting on a database D. And the other one's called the alternative hypothesis, age 1, which was that the output was generated by the mechanism acting on the database D prime. Now, F differential privacy expresses the lower bounds of the type 2 error, which we call beta, for any given level of type 1 error alpha of the most powerful test between these two hypotheses. And this mirrors a fundamental result in mathematical statistics, which is called the Neyman-Pearson lemma. Now, for the purposes of our work, we will denote the complement of the lowest achievable type 2 error at a given level alpha as the adversary's supremum power. And the reason for that is that 1 minus beta is usually called the power of a test in hypothesis testing. And P of alpha, with its calligraphic P, will be our symbol for the supremum power. Let me also talk very briefly about reconstruction robustness. That is a probabilistic data reconstruction attack guarantee from prior work. And the idea here is that we have an adversary and they have a prior pi. And you can think of pi as sort of the probability of a successful reconstruction a priori, meaning without seeing the mechanism output. And one way to conceive of this would be, for example, some auxiliary data in form of an attack database D. Now the adversary observes a mechanism output, which I've called W, because this can be, for example, the weights or the gradients of a neural network. And this is generated by our mechanism, which is acting on all of the data which is already available, but also an additional point X star. And X star is the target of the reconstruction attack. So the attack attempts to reconstruct this point, and it generates some candidate reconstruction X. Now we measure the success of this attack through a similarity or a distance between the generated candidate output and the actual point, which is the true sort of point which is being attacked. And optimally, we of course want this distance to be large. So what ReRO does is it gives a probabilistic bound on this distance being small. So basically, it says that the probability of the distance between the candidate reconstruction and the actual point being small must be very low. That means that sort of the probability of getting a good reconstruction should be very low. Let me show you our main result next. Our main theorem says something really simple. That is that if a mechanism bounds the adversary's supremum power, then it automatically satisfies P of kappa of eta rho for any prior kappa. So we basically just plug in the prior into the supremum power. As a corollary of that, we get that mechanisms which satisfy F differential privacy automatically also satisfy eta 1 minus F of kappa of eta rho. And due to the duality between F differential privacy and epsilon delta dp, we get that we also have a bound on rho through epsilon delta dp. Now, this allows us to reason about the successive reconstruction attacks in terms of statistical power analysis, for which really powerful tools exist and have existed for many years. It also reveals a very deep theoretical connection between rho and hypothesis testing dp. And this is interesting in its own right because it also explains why Renyi dp is sort of deficient at lower bounding rho. Renyi differential privacy, as you may know, does not have a natural hypothesis testing interpretation. Thus, the prior work's bounds on rho through Renyi dp have always been somewhat loose. Let me show you some of our experimental results. Since we are able to now compute rho bounds very efficiently using the aforementioned software tools, we can essentially employ tools for numerical differential privacy accounting to bound rho. And we can do that even for very large-scale workflows, whereas prior works had to rely on Monte Carlo techniques. And this is really untenable for very low sampling rates or for a very high number of compositions, because we need vast amounts of Monte Carlo samples and the variance of the sampler becomes very, very high. So now we essentially can procure rho bounds even for ImageNet scale workflows, and on the right, you can see some examples. One of them is bounding just the Gaussian mechanism, which is a very nice closed form hypothesis testing bound. And then on the top right, you can see a bound on the sampled Gaussian mechanism using either numerical techniques or some approximation using an Edgeworth series, which has been used traditionally to do power analysis. And on the bottom, you can see two results from the recent paper of D et al. From Google DeepMind. These are the parameters that they used to train ImageNet, 16,000 points in a sample and 71,000 steps. And on the right, the bottom right, we've got an even more extreme kind of scenario where we've got only 128 samples in a batch or in a points in a sample and many more steps. So this just works seamlessly and allows us to actually bound these the probability of a successful data reconstruction attack. And as you can see, the probability of a successful attack in the case of ImageNet for a prior kappa, which is 10 to the minus 2 on the bottom left, is really close to 0. So even with kind of relatively weak DP guarantees, which you need to train ImageNet successfully, you've got a very strong bound on the success of such a data reconstruction attack. So that's all from my side. Thank you very much for listening. You can contact me at the email below, and I would love it if you read our paper and gave us some feedback, and I hope to see you in person next time. Bye-bye.